Calculus 2.4, continuity is the last section of chapter 2 that we do, and then it's just a matter of doing some homework stuff and some sheets and reviews and eventually a test. So today is about a thing called continuity. To explain this in basic, easy, simple words, continuous curves can be drawn with one continuous motion of the pen. So if I make you a sine graph, that is a continuous curve. If I try to draw from the other day the graph of 1 over x, this part is continuous, but then there's a discontinuity because I have to lift my chalk, and we had another thing up there. If I do a graph like x squared, that's continuous. I didn't have to lift my chalk. But if I do 1 over x squared, that's a funnily looking graph. I have to lift my chalk because there's two branches. This branch is continuous within itself, but it's discontinuous from the other branch. That's the idea of continuity. This being calculus, they've decided to create some specific definitions beyond just like a basic word that you could justify with math, and it ties into things from this chapter. So this is a 3-part rule. You have to obey all the rules to be continuous. First of all, the function has to exist. So we got back to function values from the first day. Function values on the first day were the days where you were looking for the filled in dots to see how high they are. So I'm going to step to the right here to look at this graph a little bit. You have this graph in your hands already, I think, on a notes paper. Am I still being shot when I step to here? Good. Okay, so for this, I did the dots so far, but not the curves. You know, at 0, we have a filled in dot. At 1, we have a filled in dot. At 2, we don't. So already, before I even draw the curve, there's a continuity problem at 2 because there's not a filled in dot. At 3, there's not. At 4, there's a filled in dot. At 5, there's a filled in dot. At 6, there's a filled in dot. But at 7, there isn't. Okay? So 7 has an issue with the function existing. That's a thing that has to happen. The function has to exist. Second thing that needs to happen is the limit has to exist. For the limit to exist, it's where the spider walking on the two sides arrives at the same location. The two branches join. If there's a high road compared to a low road, that's the limit does not exist. This would be a limit not existing moment because there's a high road and a low road. And when I draw my branches over here, we're going to run into that. So like this, there's a little bit of a low road coming in, and then there's a high road. This is a moment here where the limit doesn't exist because those two branches didn't connect to each other. From 2 to 4, there's something sort of like that. Keeps going up to there. Come on back down. We're over here. Here's another part that's disjointed with a low road and a high road. Those don't mesh, so that's a limit does not exist kind of moment. Basically, everywhere I would have to lift my chalk is a discontinuity point. So if I graph this from the beginning, I'm good. Lifting, 1's a problem, and I'm up here. I follow through. I did something wrong there. I was supposed to connect to there. Okay, so I'm to here. I had to lift. Trace. Had to lift. Keep traveling. I have to lift. And then I finish there. This was an this was an so was that, so was this, so was that one. That's my sort of moments. Third problem is the limit has to equal the function. Okay, so even if the two branches are going like this, for the limit to exist, then if the dot is astray up here somewhere, now the limit and the function are in two different places, that's still a problem. So what the homework will ask you to do on simpler graphs than this is one mega crazy graph that shows you everything. They'll do simpler graphs and ask you to identify where is this continuous, and they'll ask you why not. So your answer is generally, this is continuous everywhere except. So if you said to me, where is this continuous? I'd say everywhere except 1, 2, 4, 6, and 7. 1, 2, 4, 6, and 7 are our discontinuity points. And if they ask, why is it discontinuous? You go to one of these 3 rules. rule 1 for the function existing means we struck out on the filled in dots. So if I want to skim for that, function not existing is here. So at 2, we're discontinuous because the function doesn't exist. There's no filled in dot here. And at 7, that's like that rule number 1, function did not exist there because there's no filled in dot. If I look for limit not existing, that's going to be where we get high road, low road. So this, we've got a disjointedness there, so that has a double problem. Okay, the function didn't exist and the limit didn't exist. That really struck out. This is another one where it's got a high road and a low road, so that's an answer discontinuous at 6 because the limit doesn't exist. And then the ones I didn't do yet, there's probably one left over there. The limit didn't equal the function for this one at 4. The limit existed because the spiders coming from the right and left are both headed to a limit of 2, and they agree with each other, left and right. There's a unity there. But then the filled in dot for the function value is located elsewhere. So that would be an example of that. So that's the concept of continuity. Then there is an extra bonus word is if you have a scenario where the limit did exist. Some of the discontinuities that we just looked at are called removable discontinuities if the limit existed. So at 1, the limit did not exist, and I didn't mark that one over here. That fell under rule 2. At 1, the limit did not exist, so that discontinuity is not removable. At 2, the limit did not exist. That discontinuity is not removable. At 3, this discontinuity is removable because the limit existed. One way to think of this is it's kind of a simple fix. If we wanted to fix this graph, you basically just have an issue with this stray. And if you could just kind of walk along and go, think, you know, all you'd have to do is fix that one little baby hole. That's not a tough fix. That's called a removable discontinuity. This is not removable because the limit didn't exist. We've got these 2 roads, they don't meet each other, there's no easy fix for that. At 7, this is a removable discontinuity because the limit doesn't exist. When we're at the end, we just need the one spider coming from the left to have a place to go. To fix this would basically amount to filling in that dot. You know, if you fill in that dot, that would be fixed. That would be a removable discontinuity, like if you missed it by a point. So removable on that was 7 and 1. The solution, or no, 7 and 4. The solution at 4 would be fill that in. At a height of 2, just fill it in. The solution here, a height of 1, just fill that dot in and we'd be good. Those are called removable discontinuities. Some of the homework won't work from graphs, they'll work from equations. So if you're working from an equation, what you have to do is think of some x's that can make the y, or the f of x, be impossible. So something like this, you can tackle this one of 2 ways. Fractions, you remember hopefully that you're not allowed to have the bottom 0. So one way to tackle this is just figure out what could make the bottom 0. So you could either set up an equation like this, equals 0, get the x squared alone. Opposite of squaring is rooting. It gets you not just 2, but negative 2. Or more likely, you go factor the bottom, and you come out with 2 and negative 2. They're going to ask you, where are the discontinuities? If they say, where are the discontinuities? That's where the discontinuities are. Something you can sometimes do to these problems to solve the issue is, while you're in the factoring mode, factor the top also. And the x minus 2 could cancel. This 2 would be called a removable discontinuity, to go back a topic, because it was fixable. Okay, the 2 was an issue in the original form, but by a little factor canceling, the 2 isn't really an issue in the long term, because if we're insistent on wanting an answer to go with 2, plug 2 into who's left, and if you plug 2 into who's left, it could create 5/4. So one thing they'll have you do in the homework is create what's called an extended function, I believe is the vocabulary for this, is the original thing was equal to this problem. But for that problem, we shouldn't use 2 or -2 when we're in that form. However, we can add on a second level and extend this, because if x is 2, that was removable. And plugging in 2 into our factored canceled friend got us 5/4. We were able to solve one of those two issues. We don't build a level for the -2 because that wasn't solvable. That -2 is just, it's a lost cost. There's no way to do anything with that. But that's the notes, and then my paper says to do 3 problems usually, so here's 3 problems from the homework. Homework, we're working page 99. We're working 1 through 12, which is pretty much all graph-based, mini graphs like my mega graph. Then jumping in on 19, they ask you to find points of discontinuity. So for 19, again, there's a fraction in an equation, so you look at that and think, is there any way that I could make this bottom 0? The bottom being 0 would be if we stuck 2 in there. So I'm not sure, you can check the back of the book. They might just want a list of numbers and just say like 2 is bad. I think it's more likely they're going to want you to say that x shouldn't be allowed to equal 2. I think it's more likely that's going to be the style how they're going to want you to write the discontinuity, like I did up here. X is not allowed to equal certain things. Check the back, see what they do, just do what they do. It's not super crucial, but there might be a list, or it might be like, hey, don't let x equal these numbers, kind of a style. Up to 33. 33, they're doing one of these extended function kind of moves, but they're spotting you most of the work. So they're saying f of x equals squiggly brackety thing, x squared minus 1 over x minus 1. Oh, by the way, x shouldn't be allowed to equal 1. Now create a new level where we insist on solving it for x equals 1. They spot you all of that. You just have to do the math to come up with like what we did with the 5/4. So you factor the top, x minus 1, x plus 1. You could then cancel the bottom, the x minus 1. X plus 1 left standing, 1 put into that. You're just after the 2. For number 33, I don't think you have to write out all that stuff. Like they spotted you all that stuff. I think you're okay, check the back, see what they do, but I think you're okay just saying 2, all right? For 37, you're gonna have to do, the answer will be the full thing. Okay, so you're gonna say f of x equals, they give you this fraction. What you're gonna do then is build some levels. On level 1, you have to decide who is the bad boy x number. Okay, x is not allowed to equal 2, because that would make the bottom 0. Sometimes there's more than one problem number, sometimes there's only one. Let's just have one. Then build a new level. If x is equal to 2, then you have to think about what you'd want the answer to be. If we try to plug in 2, it's the sine of 0 over 0. And hopefully you remember from yesterday that the sine of 0 over 0, by rule, sandwich theorem working in the background, was 1. We wouldn't make a fraction out of this because there aren't really any coefficients. If they had like a 5 there wanting to distribute, now your answer would have been 5. Or if they threw in a 6 wanting to distribute there, now your answer would be 5/6. They didn't do that, so the answer is just 1. In any case, the x minus 2 would have made 2 be the bad boy number. We'll take those out there because that wasn't really a thing. That's it for chapter 2.